So, good morning, everyone. I'm Haoyu Peng, and now I'm an enrolled master student from the University of Tokyo. And today, about my presentation is about the analysis of local strain non-uniformity in reinforcing bar in concrete using digital image correlation. So let's start my presentation. Bound behavior is an important property of RC structures. As we all know, it can prevent steel bar from pull out from massive concrete and have been studied by many researchers. For example, Professor Goto has studied the internal crack in concrete during the pull-out test, and Professor Shima also modeled the bound slip strain behavior. And Dr. Okio also visualized the local bound behavior using digital image correlation technique. In addition, the rebar corrosion can change the cracking pattern on the surface of RC beams, and it can also affect the response of the deflection. This means the shear carrying mechanism of reinforced concrete beams with steel corrosion is changed due to the bound deterioration. So in order to accurately study the bound behavior, the RBSM simulation was introduced. In the RBSM, the fracture and stress condition could be accurately simulated, and this is because the element in RBSM is interacting through one normal spring and two shear spring between them, and it's basically a DEM method. Therefore, the behavior of rebar in SM is quite different from that in reality, since the rebar behaves discretely here. So if we input the constitutive model obtained from the experiment, for example, the Professor Shima's model, to simulate the pull out of rebar in RBSM, the result of the post-year bound behavior is very different from the experimental result. And for this phenomenon, we guess non-uniform strain might occur in very local scale in steel bar due to the local bound. Like in the post-year range, some part the rebar is already yield and some part isn't. And we cannot simulate it in current RBSM model because the current mesh size is still not fine enough, which influence the stress transfer between the element in RBSM and also our simulation result. So to solve this kind of problem, first we need to directly observe the local strain. However, the current measurement method, like the traditional strain gauge, cannot provide detailed information of local strain because it still shows an average strain at the length of a strain gauge. Therefore, my objective in this research is to figure out the local strain distribution inside steel bar using digital image correlation technique, which is a powerful tool for studying the local deformation of the structure. So in DIC, the different strain values marked as different colors as shown in these figures. And I also would like to investigate the effect of rebar corrosion on the local strain distribution. This analysis is mainly based on Dr. Kuma's experiment, but he cut a window in the middle of the specimen for the observation, and the steel bar is pulled out, and the video was taken during the loading test for analysis. However, in his analysis, he mainly focused on the internal crack in concrete and interface behavior, rather than the strain inside the steel bar. And in my analysis, the rebar with 3 different corrosion degrees was used, which is uncorroded 12% and 20%. And now I would like to introduce my analysis. The top side figures in this slide is the strain distribution diagram of uncorroded case and in different load level in DIC software. I set 5 calculation lines along the longitudinal direction and from near the interface to the internal part of rebar. We can see the black line is nearest to the interface, and the red line is almost in the center of the rebar. In DIC software, we can easily obtain the strain distribution along these lines. So then the strain distribution was calculated, and the result is shown in the bottom side figures. So we can see this result. When the load is 40 kilonewtons, the strain is relatively low and quite uniform. When the load increased to 80 kilonewtons, some part of the strain is not uniform, but some part, for example, the right hand side, it's still uniform and relatively low. then the load continued to increase to 84 kilonewtons. The strain is totally non-uniform in the observation window. We can also observe that the location of the peak strain value in the black line is correspond to the location of the rib tip. In addition, the strain distribution along the red line, which is in the center of the rebar, is flatter than that in the black line. This means this non-uniform local strain only occurs near the interface. So this phenomenon, I think, is caused by the compressive force transfer from the concrete at the rib tip. As Professor Goto has pointed out, when the primary crack and internal crack occurs in the concrete at the rib tip, the side near the primary crack is compressed. And however, this in the elastic range, the rebar is not easy to deform compared to the posterior range. Therefore, this compressive strength cannot induce local strain change before the rebar yields. However, in the posterior range, the steel bar is easily deformed, and this stress can cause a stress redistribution in the posterior range and cause the local strain change in the posterior range. This slide is for the strain distribution of different corrosion degrees, which is 0%, 12%, and 20%. By using the same method as it does in previous slide, we can obtain the strain distribution along these calculation lines as shown in the bottom side figures. We can see as corrosion degree increase, the local strain becomes uniform, especially in 20% case. This is because as the corrosion degree increase, the rib profile is changed, which results in the reduction of rib height and the dip angle. For given local bond stress, the component of the compressive stress is smaller in lower rib tip. Therefore, in average, the local strain is highly corroded case is more uniform. This slide shows the increased trend of the strain below the rib tip and the strain below the flat part. The red point in the top side measures the rib tip strain, and the average strain value at the white point represent the flat part strain in bottom side graphs. It is observed that in uncorroded and 12% case, the strain increased together until the strain value reaches 1.5%. After that, the rib tip strain is higher, meaning that the non-uniform local strain occurs in the reinforcing bar. However, in 20% case, this non-uniform trend is delayed. The rib tip strain isn't higher than the flat part strain until the strain reaches 2.5%, as seen by this red curve. And this delay of the non-uniform strain is caused by the corrosion product around the rib profile of the steel bar. As discussed in previous section, the non-uniform strain in steel bar is caused by the local bound stress transfer from the concrete side. In uncorroded and 12% case, there is no observable corrosion product. Therefore, the stress could smoothly transfer to the steel bar once the load increased and the non-uniform strain occurs after the rebar yield. However, in 20% case, the corrosion product around the rib tip prevents the stress transfer at the interface. Once the slip increases to a certain level and the mechanical interaction is initiated at the interface, the strain could smoothly transfer, and the non-uniform local strain occurs in the steel bar. So therefore, until now, the non-uniform local strain is directly observed in DIC technique and analyzed. The mechanisms also analyzed. The conclusion are as follows. And I think that's all of my presentation. Thank you very much for your kind listening.
Thank you so much, Haoyu,
yes,
for your interesting presentation. If anyone has any question, please feel free to raise your hands. So, okay, Moto, can you ask the first question, please?
Yes, how are you? Thank you very much for your presentation. It's very interesting. It's interesting to look at strain distribution inside rivers. You know, many people look at strain distribution in concrete surrounding the rivers, but it's interesting to look at these kind of strain distribution inside rivers. My simple question is, usually for DIC analysis, people need to make like black and white specular patterns. Did you make those patterns on this or not?
Yes, as we carefully checked the initial picture of the for analysis, we observed that in the steel bar, there are already some white and black points inside there, onside there. So there is no other need to attach new white and black points to increase the accuracy. And accuracy is, yeah.
I see. You didn't need to use any spray or something to make speckle pattern. Just patterns of the rebirths themselves work.
Yeah.
Okay, interesting. Did you check the analysis accuracy?
Yes, I think in the DIC software there is a tool to help us check the quality of the image itself, and it turns out quite high, and I think it's convincible. The result itself.
I mean, is it possible to check the analysis accuracy from let's say using another type of method, another type of data, for example? For example, you know, the macroscopic total strain of rivers from the applied load, and if you integrate the strain distributions along this line, I mean the data from the IC, can you say the data are almost the same?
Maybe
comparing macroscopic strain and the calculated total strain from the IC data. That's what I meant.
Oh, I see. Maybe currently we are only using this kind of tool to replicate the result we observe in DIC. So maybe we don't consider to we checked the results in the experiment, but we are using RBSM to replicate our DIC results.
I see. As long as you compare the trend in different series, I think it's okay. But if you want to look at the actual numbers, values of the measured strains, you may want to check the accuracy by using another method. Thank you.
Okay. Thank you. Thank you for your question.
Thank you so much. Does anyone has an additional question for Haoyu? So I can ask a general question. So when design a structure, when we account for the strength of the rebar, we assume the uniform distribution of strain. So we consider the yielding force as the yielding tensile strength times the area of the reinforcing bar. So what are the consequences, or what could be the consequences of having this non-uniformity in the design? What is your opinion in that sense?
As I introduced in the background section, we are trying to why we are trying to observe this kind of phenomenon is because we find some difference between the experimental result and the simulation result, and because of the in the current model we use this kind of model size, and it cannot replicate this kind the very detailed strain distribution in the reality. So but we don't have any fact to support our ideas. So firstly, I think we need to directly observe it in reality. Then it can support our idea to improve our RBSM model to further improve the simulation framework of pull-out behavior of the steel bar. That's our opinion, and to why this research goes.
Okay, fair enough. Thank you so much for your explanation.